On a bright, sunny morning in Hawaii, the ground suddenly shifted 8 meters in minutes. The coastline dropped and the ocean surged inland. A magnitude 7.7 earthquake tore through the south side of the Big Island, and there was no volcanic eruption in sight. It was the land itself sliding toward the sea. But here's what's deeply unsettling. The system that caused this never stopped. GPS instruments show the entire south flank of the Kilauea volcano still creeping seaward, forced outward by magma rising beneath it. Ancient mega-landslides reveal that this volcano has collapsed before. If it happens again, the ocean won't wait. A tsunami would strike Hawaii in minutes. The question now isn't whether the island is moving, it's how far the next shift will go. When most people think about Hawaii, they picture lava fountains, black sand beaches, and glowing rivers of molten rock flowing toward the sea. They imagine eruptions rising upward, dramatic and visible. But volcanoes do not just grow vertically, they also spread outward, and sometimes they fail sideways. On the southeastern side of the Big Island, along the slopes of the Kīlauea volcano, an enormous section of land is slowly shifting toward the Pacific Ocean. Scientists call this unstable mass the Kīlauea slump. It is not a simple crack or narrow fissure you can step across. It is a vast portion of the volcano's south flank, stretching from high on the mountain down across the coastline and far beneath the ocean surface, descending thousands of meters underwater. It is not the entire island that is unstable, but an enormous section powerful enough to redraw the coastline if it ever gives way. Kilauea was built by a deep mantle hotspot that has poured lava onto the Pacific plate for hundreds of thousands of years. Layer upon layer of hardened basalt stacked into a massive volcanic structure. As it grew, it became extraordinarily heavy, pressing down on thin oceanic crust already bending under the weight of the island chain. Beneath the south flank lies a nearly horizontal detachment fault, a weak, slippery surface separating the volcanic pile above from the oceanic crust below. Magma pushes the south flank outward from within, while gravity pulls the heavy slope toward the sea. From the cliffs of Napali, the land feels solid and eternal, yet that entire slope is gradually shifting seaward. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. Beneath the surface of Kilauea, pressure is always building. Magma rises from deep underground and intrudes into long fractures known as rift zones. As it forces its way into these cracks, it pushes the surrounding rock aside and drives the volcano outward from within. Every pulse of magma increases internal pressure, and that pressure has to go somewhere. When magma moves into the east or southwest rift zones, it pushes against the south flank. The movement is subtle but measurable. GPS stations anchored into the ground show that the flank creeps more than 5 centimeters toward the ocean each year. It does not sound dramatic, but multiply that by decades, and you realize the scale of displacement accumulating. This motion is uneven. It accelerates during eruptive episodes, when magma pressure spikes. It slows when the system is quieter, but it does not stop entirely. The south flank is mechanically linked to the magmatic plumbing of Kilauea. As pressure builds below, the slope adjusts above. For long periods, the movement is slow enough to escape daily awareness. Yet along the buried detachment fault, strain continues to accumulate. Rock resists until it cannot. And when that resistance breaks, the motion is no longer measured in centimeters. Sometimes it happens all at once. On November 29, 1975, the south flank of Kilauea snapped. A magnitude 7.7 earthquake ruptured along the detachment fault beneath the volcano. In a matter of minutes, parts of the Kīlauea slump shifted up to 8 meters toward the Pacific Ocean. Sections of the coastline dropped several meters, cliffs fractured. The ocean responded almost immediately. A tsunami surged along parts of the Hawaiian coast, reaching heights of more than 10 meters in some areas. 2 people lost their lives. Boats were torn from moorings. Infrastructure was damaged. The island had physically moved. This was not a flank collapse into the sea. What happened was a sudden release of accumulated strain along the sliding surface beneath the volcano. The block shifted, the fault slipped, and energy that had been building quietly for years was discharged in minutes. The most unsettling part is not the violence of that event. It is the realization that it was only a partial movement. The system did not fail catastrophically. It adjusted, it reset, and then it continued. The south flank did not become stable after 1975. It resumed creeping, magma kept intruding, and pressure kept accumulating. The event proved something critical. The hilliness slump is not theoretical. It is not a computer model or a speculative scenario. It is an active, dynamic structure capable of sudden, powerful movement, and it is still connected to a living volcano. Nearly 5 decades after the 1975 earthquake, the south flank has not locked into place. Modern GPS networks, far more precise than those available in the 1970s, show that the Helena slump continues to inch seaward at rates of roughly 5 to 10 centimeters per year, pushed outward by volcanic forces and pulled by gravity. The 2018 eruption of Kilauea underscored this connection when a magnitude 6.9 earthquake related to magma movement nudged the slump by about 2 feet, and instruments recorded measurable seaward displacement during that episode. This relationship keeps scientists alert. The detachment fault beneath the volcano is not isolated. It responds to the volcano's internal cycles. When strain accumulates along the detachment surface, it can release in earthquakes. The system is not dormant. It is active in slow motion. Stand on the south coast today, and nothing looks unstable. Yet beneath that calm surface, stress continues to accumulate. The earthquake of 1975 was not the end of the story. It was part of an ongoing cycle. The most dramatic question surrounding the Helena slump is simple and unsettling. What happens if the entire south flank collapses? If a massive section of Kilauea's southern side were to detach suddenly and plunge into the ocean, it would generate an enormous submarine landslide. That displacement of water could trigger a tsunami far larger than the one produced in 1975. Early modeling studies suggested that waves near Hawaii could reach devastating heights under such a scenario, with simulations projecting waves of up to 20 to 30 meters striking parts of the US West Coast. Energy from such an event could radiate across the Pacific, reaching Japan, Australia, and even South America. The imagery is difficult to ignore. A towering wall of water racing toward shore, coastal communities overwhelmed, harbors destroyed, shockwaves rippling outward across thousands of kilometers of open ocean. This scenario gained attention for a reason. The seafloor around Hawaii bears the scars of ancient flank collapses. Vast offshore debris fields showing that enormous sections of volcanic islands have failed before. These were not small landslides, but colossal mass movements that reshaped the ocean floor. Those scars prove that giant collapses are not impossible here. They have happened before. Modern research, however, paints a more complex picture. Detailed studies indicate the south flank is not a single rigid block poised for one catastrophic plunge. Instead, it appears segmented, moving in increments through repeated slip events along the detachment fault, rather than a whole collapse of the entire flank. That does not eliminate risk. While a total sudden collapse under current conditions is considered unlikely by many scientists, large magnitude 7 to 8 earthquakes along the south flank remain entirely plausible. Sudden coastal subsidence, where sections of shoreline drop relative to sea level, can occur during these events. Local tsunamis can be generated by abrupt seaward displacement, with waves exceeding 14 meters impacting parts of the Big Island's coastline and sending surge across neighboring Hawaiian islands. Infrastructure along the coast could be damaged significantly. The Helena slump does not need to collapse entirely to cause disaster. It only needs to slip. The Helena slump is not being ignored. It is monitored constantly. GPS stations anchored across the south flank measure movement down to millimeters. Seismometers record tremors along the buried detachment fault. Satellite radar scans from space, detecting subtle deformation invisible to the naked eye. Scientists track how magma movement affects the flank in real time. When the ground accelerates, they know. Preparedness extends beyond instruments. Hawaii has tsunami warning systems, mapped evacuation routes, and emergency protocols shaped by past earthquakes. The memory of 1975 still informs planning along vulnerable coastlines. But monitoring does not mean control. The south flank continues to creep. Magma continues to intrude. Stress continues to accumulate beneath the volcano. The system is understood, but it is still active. And while the instruments can measure every centimeter, they cannot predict exactly when the next significant shift will arrive.